in this video we're going to be doing Calc AB problem set 121. The problems and a playlist are in the description below. Let's look at the problems. So first up, graphs of y equals 2 the absolute value of x minus 1 plus 1 and y equals negative 4/5 absolute value of x minus 2 plus 7 intersect at x1 and x2 with x2 greater than x1. Write an expression involving one or more integrals that gives the total area of the shaded region. Okay, so x1 is less than x2, so this must be x1. That must be x2. Because I don't want to have to write those over and over again, this is a good idea. I'm going to name the function. So I'm just going to say f of x is 2 absolute value of x minus 1 plus 1, and that g of x is negative 4/5 absolute value of x minus 2 plus 7. Now I will use those in my answer. So we're just going to go through and we're going to make sure that we're doing top, take away, bottom, and on the correct interval. So first interval is negative 3 to x1, and on that interval, the one that opens up is on top, so f of x is on top. So negative 3 to x1, top is going to be f of x, and then bottom is g of x, so f of x minus g of x. Then between x1 and x2, the one that opens down, g of x is on top, so it'll be x1 to x2, g of x minus f of x. And then from x2 to 5, the one that opens up is on top again, so that's f of x, and then the bottom will be g of x. So from x2 to 5, and we said f of x minus g of x. There you go. That's all you have to do. You don't have to evaluate it or anything. I also think you could, so like if this was multiple choice, there's no way to know how this would go. You can get this answer by just doing the integral from negative 3 to 5, the absolute value of f of x minus g of x. That's like the slick way to do it. It's not really the way that your teacher will probably ever mean for you to do it. But if it's a calculator question, there's nothing stopping you, other than the fact that sometimes the calculator can't really handle it. All right, number 2. Find the area of the region between y equals x squared minus 4x plus 5 and y equals 2 on 0 to 5. Okay, so let's start with a picture of this thing. So we got a quadratic. We need... at x equals 0, that first thing is 5. So I put 5, and then y equals 2 is the other line. So I'm going to figure out the vertex of this thing just by using a derivative, right? So I took the derivative, set equal to 0, I get 2. That's where the vertex is. If I take 2 and plug it in, I'm going to get that y at x equals 2 is 1. So now I know basically how to graph this thing. So 2 are at 1, and then by the time you get to 5, you're like way up, right? Because by symmetry at 4, you would be at 5 again. So when you're at x equals 5, you're higher. And then we have this at y equals 2. And then our regions, so I'm going to kind of color code a little bit here. We have quadratic is above, and then linear function is above, and then quadratic is above again. That's what we're dealing with. I need to know the intersection points. So I'm going to set the two curves equal, move everything to one side, factor, and then find the zeros. So the zeros are at 1 and at 3, so that's where these curves intersect. All right, so what are we going to do? Well, I think what I'm going to do is a little bit weird. You can set up 3 definite integrals and just do the problem, which is maybe a more normal way to do it. What I'm going to do is I'm going to find kind of that purple plus yellow area, I guess, by doing the integral from 0 to 5 of just the quadratic. So that's everything. It's everything except the blue area. So I'm going to do 0 to 5 of the quadratic. But then I've overcounted by like kind of a lot at this point, basically a rectangle that is 2 by 5. So I'm going to subtract that off. And then I subtracted off the blue region, which I had never counted. So I have to add that back in. So I'm going to add in the integral from 1 to 3 of x squared minus 4x plus 5. So that's like, this is a complicated way of doing it. I don't know why I decided to do it this way. You could have just done 0 to 1 of top, take away, bottom, and then 1 to 3 of top, take away, bottom, and then 3 to 5 of top, take away, bottom. If that's how you want to do it, you will get the answer. I don't know. I decided to do it this way. I'm going to do each of those integrals separately. So this integral, reverse the power rule. So 1/3 x cubed minus 2x squared plus 5x. Use the fundamental theorem, so you're plugging in 5. When you plug in 0, you just zero it out. So plugging in 5 gives us 125 over 3 minus 50 plus 25 and then minus 0. So that simplifies to 50 over 3. Then we'll do the blue integral, so from 1 to 3. So reverse the power rule. It's the exact same function, so you get the same antiderivative. Going from 1 to 3 this time. So fundamental theorem, plug in 3, we get 9 minus 18 plus 15. Plug in 1, we get 1/3 minus 2 plus 5, but we're subtracting. Simplify that, we get 8/3. So overall, I'm getting 50/3 and then minus 30/3, which is that 10, and then plus 8/3. So my answer to this is 28/3. If you did it a different way, see if you get the same answer. I think you will. All right, next up. Find the area of the region bounded by y equals x cubed plus 3x minus 1 and its secant line on the interval from 1 to 2 with a weird, awkward line break there. All right, so I got to write the secant line. So I need to evaluate this thing at 1, which gives me 3, so ordered pair 1, 3. I need to do the same thing at 2, because to write a secant line, I need the 2 points. So I get 2, 13. So that means the slope of the secant line is going to be 13 minus 3 over 2 minus 1, so that's 10. So my secant line is y minus 3 equals 10 quantity x minus 1. All right, I also need to figure out if the secant line is above or below the curve. I'm going to use the concavity of the curve to determine that. So I'm going to find y prime, which is 3x squared plus 3. I'm going to find y double prime, which is 6x. So I know that when x is greater than 0, y double prime is positive, which means that the curve is concave up on this whole interval that I'm interested in, and so the secant line will be above the curve. We're kind of dealing with this. So when we do top takeaway bottom, it's secant line minus curve. So I'm going to go from 1 to 2 of secant line minus curve. So top takeaway bottom. So I move the 3 to the other side. 3 plus 10 quantity x minus 1, that's the secant line, minus quantity x cubed plus 3x minus 1, that's the curve. I'm going to combine things here. I get 1 to 2 of negative x cubed plus 7x minus 6, reverse the power rule, negative 1/4 x to the 4th plus 7/2 x squared minus 6x. We're going from 1 to 2. So fundamental theorem, first plug in 2, and then minus the quantity, plug in 1. Gives us this. A little bit of arithmetic, a little bit more. I finally got 3/4. So I apologize that I'm not like showing or like letting you watch me write it, but this problem set ended up kind of long, and I like to finish these in under 10 minutes. So got to skip the steps where I'm actually writing, but I am explaining it. So if you want to slow it down and listen again, you can hear it as I go through it. All right, and then finally, if f of x is x minus 3 over x plus 3, where x is between 1 and 3, we want to find the area of the region between the secant line on the interval and the tangent line at x equals 3. Okay, so again, we need the secant line. So I need the slope, which will be f of 3 minus f of 1 over 3 minus 1. I get 0 minus negative 1/2 over 2, which is positive 1/4. We know that the ordered pair at 3 is 3, 0. So our secant line is y equals 1/4 quantity x minus 3. We also need the tangent line. So to get the tangent line, I did something that I think is helpful. In the numerator, I added and subtracted 3, which makes the numerator x plus 3 minus 6. And x plus 3 over x plus 3 is 1, so I can rewrite the function as 1 minus 6 over x plus 3. I did that because it'll make it easier to find f prime. I'm using the chain rule instead of the quotient rule, which I think is faster. I need to find the slope, so f prime of 3 is going to be 6 over 6 squared, which is just 1/6. And at 3, we know the ordered pair is 3, 0. So our tangent line is y equals 1/6 quantity x minus 3. Now we need to figure out which of these is on top on the interval from 1 to 3. Keep in mind they intersect at 3. So the tangent line is like less steep than the secant line. So kind of looks like that. Also, terrible choice of colors. They look exactly the same to me now that I'm looking at them. But the tangent line is less steep. So from 3 to infinity, the secant line is on top. But actually, before you get to 3, or on 1 to 3, the tangent line is on top. So that's what we're going to be doing when we do top takeaway bottom. So we're going from 1 to 3, the tangent line minus the secant line. You can kind of like combine some things here to clean this up. Negative 1/12, 1 to 3 of just x minus 3. So I integrated that. I get negative 1/12 times 1/2 quantity x minus 3 squared from 1 to 3. Fundamental theorem, plug in 3, you get 0, plug in 1, you get negative 4, or well, you get 4, 0 minus 4. and that gives us 1/6. That's the entire problem set. I hope this was helpful, and good luck.